Hello, everyone. Thank you for coming to my presentations. The topic of my presentation is mining timestamp electronic health records with the reference sequences. My name is Ann Woods. I am a statistician at the Northern California Institute for Research and Education, the Veterans Health Research Institute. Using EHRs for health research has gained a lot of interest in the past several years. At VA, this is no exception. So what is the problem? Most electronic health records are time-stamped encounter data stored in relational databases. The table on the right contains examples of such records from different clinical domains. These records by themselves cannot be directly analyzed by statistical or machine learning software. For those purposes, the input data will need to look more like a table on the left. So what's the difference between the two tables? The short answer is that the columns on the left contains sample realizations of statistical random variables. I will call them analysis variables. Typically, data we analyze are from direct observations. The data on the left could have come from a study where medication exposure and weight were directly observed and measured. However, the records on the right could also be used to create analysis variables like those on the left. In fact, this is currently how EHRs are analyzed. And this process of creating analysis dataset is manual and time-consuming. Analysis variables are formulated by clinical investigators. The coders extract the records from the relational databases and write programs to create analysis dataset. The process is iterative because the investigators may not have the time or skills to write complicated codes to wrangle the records into analysis-ready dataset. The coders are not clinical experts and do not always know how to spot inconsistency in the data. Clinical analysis variables are also not universally defined either. They're not unique. Similar concept can be defined differently because of study aim, context, patient, cohort, or by different investigators. The thinking process of formulating clinical analysis variable is similar to how physicians will make clinical assessments from patients' medical records. They evaluate the relationships of the what and when of the records. The time gaps between records are often not missing information, rather information to be interpreted. So the problem is that EHRs are observational data, and observational data most commonly contains multiple correlations. The manual step needed to create analysis dataset is a barrier to thoroughly investigating these correlations. We believe the solution to remove or at least reduce the manual step is the ability to obtain data from any clinical domain and in any time frame efficiently. We propose a framework to do this by using two interreferable functions on data building blocks. Our medical history is continuous, even though the medical records only contain information at discrete times. Without loss of generality, we use date as the time unit, but other units can also be used. For each type of clinical information, we use time function to indicate where the information for a particular date is stored in its data block. For example, time function F1 maps a sequence of locations to a sequence of dates, starting from a reference date. The state function indicates how the information is represented and what does it mean clinically. For example, state function G1 maps 1 to mean on medication and 0 to mean not on medication. The state function can also be the identity function, like weight. The representation of weight is just weight. in some unit. In the next slide, I will describe how we obtain the values of a TI-AV. TI-AV, Time Interdependent Analysis Variable. This type of variable is common in health research using EHRs. In this example, we want to find a patient's total cholesterol level in the 30 days after a particular procedure, provided that the patient was compliant with the 2 medication regimens. We first search the code 33203 in the CPT code data block. We found it in location 5, and time function F3 maps it to March 1st, 2010. We then use the inverse of the time function F1 to locate the 30-day interval from March 2nd through March 31st on the medication 1 data block. We repeat this step for medication 2. The state function for both medications indicate that 1 means on medication. So we apply the sum function to the 30 zeros and ones to derive the total days on each medication. Since the compliance requirement of 75% and 50% are met, we move to obtain the cholesterol values. Using the inverse of time function F4, we locate the 30-day interval in the lab data block. Since the state function G4 is just the identity function, no additional mapping is necessary. We obtain the average cholesterol using the mean function. What do the data building blocks look like? The good news is that they are not prescriptive. They just have to work with the time and state functions, such that data location, time unit, data value, clinical meaning can be unambiguously determined. The examples in my paper using text strings to represent daily medication use. They can also be represented differently, as you see here with the variables V1 and V2, where V1 is the starting position of an all-one segment, and V2 is the length of that segment. Which days are ones and zeros can be determined from either implementation. Just the codes to do that are different. Once the individual values are obtained, analysis variables are made up of either the values themselves or simple statistic of them. Because analysis variables can be created using scripts to manipulate the time and state functions on the appropriate data building blocks, the analysis algorithm can be connected to the information in EHRs without, or at least with greatly reduced custom programming. This could enable automation and faster and more thorough investigation, as the investigator themselves can make inquiry and perform rapid ad hoc analysis. I believe there are needs and opportunities for method development and software development in order to more efficiently leverage the hugely rich information in EHRs. As I mentioned earlier, the formulation of clinical analysis variable has an element of subjectivity. It will be very helpful if there are methods to quantify the impact of the formulation or meta-feature selection methods that optimize the formulation. For software development, there is a need for self-service tools that investigators can use to create analysis variables, something that enables them to easily compare formulations, return cohort size by selection criteria, display demographics of subpopulations, and create exploratory graphs. This concludes my presentation. Here's my contact information. Thank you.